Alright, draft physics video, science and such. So anyway, I made this video last night, and then the camera battery went, and it's kind of funny because in hindsight it was very opportunistic in the sense that so instead of doing the video I started doing some thinking, and eureka kind of a thing happened, which is, very good. So, happy accidents all over the place all the time are required. Well, not even required, but it happens in this process and can expedite the process, or it can get in the way of the process, I suppose. I might have done something even more brilliant if I had made the video. Who knows? That's the catch. Anyway, so it's going on about the polarization bit and understanding the nature of this field, gravity. So the first point to be made, and be emphasized and made clear, is that all of this stuff, these little bits, none of them actually change direction. So the bits themselves go straight through everything. They just travel straight lines forever. So it does make for an interesting circumstance, in that there has to be something in the end of the universe that would reflect this energy, or it indicates that it's some kind of the nature of the universe. This goes like that forever. There's just this stuff moving forever at the speed of light, something like that. But I don't want to get lost in that conversation. But I'm just saying that needs to be sort of kind of understood, is that no arguments being made here that the actual things change direction. The only thing that really changes is the polarization, as I've been emphasizing. In one form or another, the change is as dramatic as the difference in the force between the positive and the negative, the electricity charge, and the difference between the north and south sides of a magnet. Clearly different forces, exactly the same mechanism, just polarization is the difference. So it's like a color or a suit or a form that the energy carries, and then it carries some other bag, it carries something else, it changes clothes, so to speak. So alright, so I've attempted to use color coding to make some of this understandable. And so what I realized, my old polarization diagrams always had something going from one color deflecting. So it would be like this idea of one polarization comes in, another polarization comes in. Instead of the polarization going straight through the interaction, it reflects. And so that's where you get this idea of change. If it went straight through, then you really couldn't tell, in some respects, whether an interaction happened or didn't happen. And it's this idea of a changed angle that makes it all kind of realizable. And then what I didn't think about, though, was that polarization has that tricky 45-degree angle where is it this or is it that? And so what I'm talking about is this is the opposite of this. So it's only a 90-degree angle difference, not 180-degree for the opposite. And the perpendicular to that, or the tangent to those two, is this 45-degree angle. So anyway, something like that is the mechanism. So this allows for there to be a circumstance where polarization comes in and it hits another polarization, and the outcome is really two polarizations that end up being in a category of their own. So it's essentially a change in polarization, and that's the nature of electrons and protons. That's their function, basically, is they're converting these interactions into a new polarization. And the inverse would be green to black, and that would produce red. So the green to red produces black, the green to black produces red. And that basically creates the opportunity for the repulsive and attractive forces in electrons and neutrons. I would say obviously the next step will be to create the proton. Protons and electrons. The neutron will likely be made out of this green stuff. And so I haven't gotten to that yet, and produce both field energies of the red and the black. So the argument would be is that electrons, let's call these electrons, would be made of this red polarization in the inside, and it essentially reflects. Like I said, the arrows actually go through each other, so let's not be deceived. All these arrows go straight line forever. But for a moment they're wearing this polarization, and then they exchange it, and that's basically what's happening, is there's an exchange made, and probably on these tangential interactions. So the interactions are probably at 90-degree angle interactions. But we don't need that for the sake of this argument. So what's happening is, say a green comes in, it hits the red, and a black is produced in both directions. So you can sort of get the idea that what's basically happening is these red bits are moving towards the outside, and they're hitting this green, what we call the field energy. So that's the gravity, that's the field pressure that always exists, and it converts it basically into this black. So the black is what the red produces when it interacts with the green, and the black is hostile to the red. So when black interacts with black, you get a reaction that is displayed here. The common, more obvious reaction. That is, the black is reflected 90 degrees, the red is reflected 90 degrees. So what's happening is they're producing a lot of this black. So a lot of green comes in, a lot of black comes out. And particularly in these directions towards each other, this black would be all reflected energy. So the black, so you can sort of feel that with magnets, is that they get more and more powerful as you get them closer to closer, is because the reflective time is increasing with your narrowing of the distance. You're doubling the amount of reflection, essentially, how fast the bits are reflecting. And it feels a lot like that. So this fits the common experience quite well, that as you bring them closer and closer, this pressure gets greater and greater and greater because it's constantly reflecting. And so that explains the repulsive force. These little arrows here just indicating that this will be the direction, the acceleration of these particles will be to get away unless they're forced and not allowed to. But that will be their natural tendency, would be to be the reflections take place, which causes the conversion of a arrow going tangentially to one going in that direction, and that would also lead to the emission of another black arrow out the sides. Alright, so in the interaction between the electron and the proton, so the proton is doing exactly the same thing as this, except it's made of black polarization. So all the bits inside of it are polarized the opposite from the electron. So this polarization for the proton, this polarization for the electron. And so the interactions with the black, with the green, produce red arrows. And obviously in this circumstance they would be repulsive in the same way, so I just didn't duplicate this in black. So you get the idea that repulsion would work exactly the same way. And but the attraction between the electron and the proton is what I'm showing here. So this one has the red center, this one has the black center, this one's producing red, this one's producing black. And the trick is that black is invisible to black and red is invisible to red. So as illustrated in earlier diagrams, if just pretend these red arrows were black, you wouldn't be able to tell that any interaction happened if they were all black. So when when same polarization meets same polarization, you get no effect because it's as if the interaction didn't happen. And so there's no pressure here. Obviously the field pressure is real because it's causing these black reflections, and the black reflections are an indication of the absorption. So anytime there's a reflection, it means there was actually an absorption, which means there was actually an acceleration. So there's all kinds of accelerating happening from the external world and no acceleration from here, because this is invisible. The red is invisible to the red, the black is invisible to the black. So nothing's happening here, everything's pushing here, and the two things are pushed together. And as these two arrows would indicate, they're getting pushed together by the field pressure. So it's like a hypergravity, essentially, in the sense that it's not just that this stuff was in some way, there's no way for this arrow to get through to this arrow. It's that it's getting through, but it's getting through as something completely invisible, rather than something that would have a half of a reaction or some other kind of reaction. It's changed into a polarization that's completely benign and therefore can't affect the thing it's going into, can't change the polarization of anything in these two items, therefore it can't change the velocity of them at all. Where the field pressure still can change the velocity, or the acceleration, cause an acceleration which will cause velocity. So that's the basics of it. I probably should put these diagrams online somewhere and for viewing and whatnot. But I thought I would talk a little bit about the consequences of this in terms of what I was talking about before about field, and the fields created by different surfaces. So a point particle will create a field in all directions, and it diverges in two planes, right? It diverges like the peacock going this way, and then there's another peacock going this way. So it has these two planes you could draw over each other, and it's spreading in both of those planes. So there's lines going this way, and then there's lines going this way. So that's not very good illustration, but we'll work on it. So anyway, it's going this way, and then there's a plane going this way. And both of those, as they go out, it gets less and less likely that you'll hit one of them. If I drew them as lines, like feathers from a peacock, and they were very long feathers, they're both diverging, spreading. So the further away I go, the less and less likely it is I'm going to be able to hit one of those feathers. And so that's the inverse square thing, the R squared rule of gravity and of any sphere or point particle. So any force that radiates from a single particle, that's what you're going to get, is the force will move through those two dimensions, and the two dimensions equals to that means that if this is your distance, at half your distance, it's 1/4 the force. 4 times the force, sorry. Jesus. The closer you get, obviously the force gets dramatically stronger, and the further away you get, it gets dramatically weaker. Now, if you have a line, like a wire, then you can kind of see that it's all a bunch of little peacocks going out. But they're all just in one plane. So there's nothing going this way, in and out of the paper. Alright, so, and you can kind of understand that if you have a charge someplace where it diverges here, it's going to, these other particles will be hitting it because they're going to diverge into it. So where this one's diverging away, the one next to it diverges into it, and this one diverges this way. So in a sense, anywhere in this height, from the perspective of this dimension, you're going to hit the same number of lines coming up. So you really can't, the lines produced by this wire, if you're perfectly straight above the wire, you would hit the same number of those lines no matter where you went if this wire were long enough. But the trick is these are still diverging, so you still have the R situation. So as you go further away, if you go twice as far, it's 1/2 the force. So instead of R squared, it's only R. And then if you do the surface, where you take a plane, flat surface and make it very, very large, and then have a charge above it. I guess I could draw that a little better so you could get the idea of it. And the charge is floating somewhere above the surface, a distance. Now you've got both, now you got both dimensions again, and you have an infinite supply. So it's like essentially having two wires and being exactly lined up with those two wires. And so no matter where you go, you'll have exactly the same charge. So the force doesn't degrade no matter what your distance is. So at any distance, the field pressure, the voltage, if it was voltage, would be the same. If it was light, it would be the intensity of the light would be the same no matter how far you were from the plane, if the plane is wide enough and long, big enough. Infinite. You shouldn't need one infinite to have the general effect be realized, as long as you're not a billion light years away. If you're a billion light years away, you're going to need a very big surface to catch that effect. So the important part of this is that when charge is created, it's through the acceleration of a particle. So when a particle accelerates, if I was using that electron as the example, and it has the red bits on the inside. Tip fell off of this thing. Well, I'll have to make do. The trick is that when it accelerates, it's going to give away some of that. So when it moves, it's going to give away force in this direction. Okay, so it's going to be giving away the perpendicular, because it's gaining this, it's changing. So it's taking polarization from the field, converting it to red in this direction, and converting this red, letting it go, and leaking a byproduct of some other color. So I won't draw it because it will be a different color. But anyway, so that's the acceleration. And the acceleration is very small as a percentage of one of these arrows. If one arrow went in, it would be 1,000,000 arrows before another arrow would go out. It's spread over the entire, all the substance in the matter has to be moved. And so it's not like one arrow equals one arrow. One arrow equals 1,000,000th of an arrow in terms of acceleration. But anyway, in the real world, there's a lot of stuff going on, and it's going very fast, and so you can have a lot of acceleration. But anyway, so when it accelerates, so the more it accelerates, the more of this energy it creates, the more it releases. And as demonstrated in the other drawing, which I will find, there it is. The electrons are, let's see, did I draw the right color? Yeah, the red, and okay, so that's right, they're converting a red going this way to a red going this way, so they're actually expelling the force as black. So that was my error. I thought that looked a little too red. So what they're doing is converting a black that comes in into a change in the red. So it changed 90 degrees this red. So you can see this little red here. It gets changed into a positive arrow from a one that was going this way, and it lets the black out the sides. So you can sort of understand that if it's releasing energy based on its velocity, so the more acceleration, the more of this that's coming out of it. You could sort of get the idea that would make these electrons even hate each other even more, because you're creating more of this energy. So if, say, this electron was moving forward, it would be even more hostile to a neighbor electron, so because it's creating even more force to be reflected. And that's why in electrical circuits, say if I have a wire, and so we're looking at the end of the wire, what happens in electrical circuits is that the charge moves to the outside of the wire. So the electricity actually runs on the outside of the wire. And when you get into high voltages, it does seem like it's out here. It's not even in the wire anymore. It's just somewhere around the wire. And the higher the voltage, the further apart they have to keep the wires, because the actual current is moving so far out. So it's the actual current is way out here, and you know, that's what's actually happening. And it's happening because the more you accelerate the electrons, the more force you create, and the more they hate each other. So unlike what conventional science might argue, is that all electrons have a charge, a Q, it's always the same. They don't. Depending on their velocity, their acceleration, sorry, it only happens during the accelerating process. Once they have velocity, nothing's happening. But while they're accelerating, that's when they're doing this, creating this extra field pressure. And so when they're getting, when they're gaining the speed, and they're constantly doing that as they constantly interact with each other, push each other along might be a way to say it, bang into each other, nudge each other. Well, anyway, the field energy goes from one electron to the next electron to the next electron. So the idea is that they sort of just push each other along. And each time they push the next guy, he's going to create this field energy. So that's why higher voltages end up going further and further outside the wire. So that was something I wanted to point out. And I don't know if there was anything else that was critical, but that all ties together. And obviously this mechanism, in my opinion, is the source of magnetism. So the very same mechanism is what's creating magnetism, in the sense that the electrons are on the surface of the north side of the magnet of the south, and then the protons are on the surface of the south side, or north, however you want to look at it. And whatever the force goes through last, you can sort of get that idea that it's kind of like whatever the arrow goes through last is going to be the thing that's the suit of clothes it's going to wear. So if the last thing it goes through is an electron, it's going to come out black. If the last thing it comes out of is a proton, it's going to come out red. And then it's going to be in the field, either red or black. And if there's some other substance that's sensitive to the red and black, which would be something that's also arranged where the electrons are on the outside and however it would be, then it'll either pick up charge, like a wire, or it will magnetize and reciprocate a magnetic field back, reflect one. And that's basically what magnets are doing, is reflecting or absorbing field energy and converting it. Alright, so that should be enough of a run through. So anyway, it's just that this does solve the problem. There are some other details of what part of this is. It's really when the black arrow goes in, kind of a thing. And what it's really reflecting off of is the field energy on the surface, and then that reflects it back in. Then it hits the red on the perpendicular and turns the red to a vertical. And so I guess the part that's not entirely intuitive is the idea that when something reflects off of a surface, that's when it's actually moving the surface. So it's kind of it's the thing that gets absorbed without a reflection that isn't going to do anything, unless it's no, that's pretty much the rule. It's the reflection. You're really hitting perpendicular dimensions is where all the action happens. So it takes two interactions to create an effect, direct effect. it's like a U-turn. Everything has to take the turn first and then turn back the other way. So to have a reversal, it's essentially going to turn it once and then turn it again. Yeah, that's probably enough. So I, you know, there are lots of little details. I don't know if I want to go through these and read them, but yeah, I think the important thing to realize is that this is just polarization. It's just a suit the field energy wears, and it's the field energy is constantly, every time it has an interaction with somebody wearing a different suit, it's likely they're going to change clothes, and so the momentum will go a different way, and I think it is kind of understandable that you could have a situation where if you have everything one polarization in an interior, that it could bounce off the field energy and stay consistent, unpolluted, until some other mechanism invades it more aggressively in some unbalanced way. Alright, so I think that's enough. I think the elements are there, and so I can proceed. Maybe I'll work on the neutron part, but I don't know whether I'll just move on to the next step. But I guess if I do the neutron, that might be it may be worth doing just to complete this scheme before I move on. But we'll see. I'm just getting sick of arrows. But anyway, just the concept's there. That's all. I'm just saying that this is the. There's been other models that have worked 90% or 80%, and this is the first. This model, I haven't found a problem with it yet. And the velocity thing is the one that kind of fools people, just because you say, well, how does this move into the field and hit more of these green arrows without that slowing it down, since these green arrows reflect the black, and it's an actual incursion. It actually causes acceleration. The green arrows cause acceleration, so how can you move through them? But the trick is, again, it's only happening on the tangents, and so the tangents, it gets smaller as your velocity increases, but more importantly, these are all these interactions. Again, this one arrow represents only a tiny bit of acceleration, so you're not accelerating one arrow forward. So there's this, you have this illusion that your speed is much greater than it actually is in terms of a real change. So our material speeds are so slow compared to the speed of the field energy, the force, that we just don't appreciate the fact that the difference isn't that, first off, it isn't like we're flying into a ton more of this thing. It would be a, you know, 1 per million more. So for every million, there'd be 1,000,001 instead. And the more important point is, what was it? Oh, yeah, when you increased your velocity, you did it first. So you had an extra, you know, when you accelerated, you gained the extra. And so you're already overcoming, because you already have an extra in the direction you're going. So you've already overcome the extra that you're going to hit, because you already have the extra. So the acceleration itself gave you extra, not an even. So you didn't start with it. It wasn't a fair fight to start with, because the acceleration was already a positive event. So the imbalance starts in the middle. I mean, the imbalance starts in the proton or the electron that's moving, and so the field is already behind, and the field is just catching up to the advantage that the accelerant caused, and so it's not neutralizing it. Watch it, cat. Anyway. So yeah, but I'll explain that more. But it's also the fish argument. They're all moving the speed of light. So from the interacting player's perspective, the field arrows, they're just seeing polarization moving through the field. The arrows aren't changing. They're not moving faster. So the arrows themselves are going the same speed. The only thing changing is the movement of the suit of clothes, and that's isn't the same as changing the momentum of the arrows. I guess that was the right way to say it. How fast the suits move really doesn't have anything to do with the momentum of the arrows. That's a better way to say it. Alright, so till next time, and such.